Okay, hi everyone. So we're about to start. Sorry for the little delay. We had some Zoom issues as always. So
it's my fault. Sorry.
So it's my pleasure to introduce today's speaker, Professor Olivier Bernard, who is now professor at the University of Lyon in the CREATIS laboratory. He's also the head of the Myriad research team, which specializes in medical image analysis, simulation, and modeling. And today's topic will be segmentation in echocardiography.
Yeah. Thank you, Christian, for this kind introduction. Hello, everyone. So yeah, today I imagine that title. So segmentation in echo, is the problem finally solved? To give you some insight on kind of work I'm doing with Pierre-Marc, who is here for well, several years now, and we have we think quite interesting result that we want to share with you. Okay, just for a brief summary of what I'm doing. So I'm working in cardiac image analysis in a translationary way, in the sense that I'm working in acquisition, image quantification, and population representation, with some keywords that you can see here in terms of methodology that you might know: segmentation, blood flow estimation, tissue motion estimation, multimodal fusion, heterogeneous data integration. And the application for that are basically those two, which is a robust estimation of existing biomarkers, and also trying to estimate new biomarkers, sorry. And the estimation, the classification of etiology, which is the origin of the pathology, and the characterization of hypertension. So today I will focus on the quantification of clinical indices to diagnose cardiac pathology. So this is the kind of data from which I'm used to work with. Oops. And here you have a very nice animation that allows you to better understand what we try to see in echocardiography. Usually people don't see anything. So, so here from the animation, you can see here at the top of the sectorial shape, this is the place where we position the probe. And this is the kind of view that we are managed to see. So you see that we cut the heart in that direction. And so this is the different structure that we managed to see. So this is the myocardium, so the muscle of the heart. We can see different chambers. So the left ventricle, the left atrium. We can see also the valves moving. So we can, from that kind of images, extracted different kind of information that are useful for the cardiologists to put numbers behind the diagnosis that they give. And so, for instance, from the sequence that you have seen, the idea is to perform that kind of segmentation in an automatic way, ideally. And from this segmentation, we can, for instance, extract the variation of the left ventricle over time, myocardial mass, ejection fraction. This is the classical clinical indices that we managed to extract. And the big difficulty is that still currently, those measurements are difficult. It's difficult to reproduce those measurements. There's a lot of source of error, variability, depending on the person that performed the acquisition, depending on the country, on the equipment that you use. So there's a lot of needs to nicely estimate those parameters. And so with Pierre-Marc, we worked a lot on that. And we will show you how we managed to do that. So this is a segmentation problem. There's a lot of methods that, and we work on that apply AI for sure to solve that problem. And one of the keys is the access of the dataset. So if you have a look at the current open access dataset, this is basically all the dataset that you will be able to retrieve and on which you can work. And if we have a closer look on those datasets, what we can see is that, so this is what I've put it in red. In terms of annotation, there are very few data sets that have the full cardiac cycle that has been annotated because it takes so much time that well, mostly no one is performing that. And also still, there is very few, almost no data set which involve multi-centers and multi-vendors. So the key aspect to go to the application of those methods in clinics are currently there. What we can say also is that since there's good data set with a nice annotation, it has been shown, and we have shown that we are able to have precise and accurate 2D segmentation on key instants of the cardiac cycle, not on the full cardiac cycle, but on key instants, results that are comparable to the intra-observer variability, which is the one which is very difficult to obtain in echocardiography, at least. And this proof for me that that kind of pilot study show that artificial intelligence is really the key to solve this problem. Okay, but the big question is it possible then to extend this work to nicely perform the full cardiac from the segmentation of cardiac structures on the full cycle, and are we able to generalize to perform well, whatever the centers, whatever the equipment, etc. So the big questions now are there, and we are working on this to solve this issue. And if we manage to prove that, then I guess that we will solve the problem of segmentation of echocardiography. Recently we have worked on 3 different data sets that I just introduced. So the CAMU, the Cardinal, and one that I named USMR. You can see the different characteristics, the number of patients, if there are annotation or not. So for instance, sorry, for the Cardinal dataset, there's no annotation. This is something that we obtained that I display here. You can see that we have GE system, but also Philly system. So all these datasets are very nice to go on this generalization process. Just to put you some numbers, so from the CAMU datasets that involve 500 patients, so this is the intra-observer variability that has been measured. So I guess you're all familiar with those metrics, the DICE metrics, I guess so. Yeah, and the Hausdorff distance, which is the maximum distance between 2 contours or two surfaces. ED and ES correspond to end diastole and end systole. So end diastole is when the heart is fully relaxed, let's say, and end systole is when the heart is fully contract. So this is 2 key instances that are important where the annotation has been performed. And so you can see that a simple 2D NN unit do the job. If you compare the result that you obtain with intra-observer variability, it's just great to see that a simple 2D NN unit is able to have very great results. Just learning from 500 patients, it's not so much, but it puts things on the good shape, I would say. So it really convinces us that we have to continue on that way, not to imaging 2 complex architectures, but more finding a way to benefit from these architectures than to solve the problem. So so this is the first step that we have done. So it's a kind of puzzle that we try to build. Okay, so we have the first piece, which is the 2D NN unit that has been learned only from 2 time instants. So of course, if you apply it then on the full cardiac cycle, you will see that. So this is very interesting because you see that the job is almost done, okay? It's not so far, but of course, you don't have any temporal consistency because you haven't tried to learn that. And the small difference that you can see is nicely explained by the intra-observer variability. Between 2 images, there are errors that happens because you cannot reach, well, the intra-observer variability is the limit that you can expect in terms of precision, but so between 2 images, you can have small fluctuation because you're inside that intra-observer variability. And the manual annotation on this image is this one. So we want to go from this to this, but we are not so far. So we could imagine to create scheme that will allow us to correct that. So this is the next step that from where we go. So how to guarantee to have anatomical and temporal consistency. Right now, I discuss a lot on temporal consistency, but also sometimes, even with an N-unit, you could have anatomical strange things that happens in few cases, but still. And it would be very great if you can guarantee that you will never have that kind of mistakes or singularities that happens. So to do that, we use the variational autoencoders framework. So I don't know if you are all used with that. It's a very common method in AI, where the idea is that starting from a data set, so here for the illustration, this is the Ncraft drawing of numbers here that you can see. You pass through an encoder to project into a low dimensional space where you hope that you will concentrate useful information. So here, to draw this, we force to have only 2 dimensions at the end, so you can nicely represent the projection of all those images. So one image is represented here by a point, and then you apply a decoder to reconstruct exactly the same numbers, and you have a very simple loss to say, okay, these numbers should be exactly the same. Well, the output one should be exactly the same as the input one, and you do that because you want to learn meaningful latent space. By meaningful, I mean that the information that you will create when you project should be meaningful to be able to reconstruct a shape that has a meaning, in fact. Okay, so by doing so and using some ideas between the terms of variational, the idea is to be able to construct a latent space with local continuity. Local continuity means that if you have a 5 number, okay, if you have the number 1, which corresponds to that part of the space, you should expect that another 1 number will be very close when you project in the space. And global completeness means that you want to avoid to have any hole in the latent space. So you can do that. Yeah, remember the next slide. So by the time that you have learned that kind of space, for instance, you can play with it. And so you can start from this point to go to this one in a linear way. And you reconstruct each time the numbers that correspond to the point on the trajectory. And you see that thanks to local continuity and global completeness, you are able to retrieve meaningful fake numbers. Okay, so this is the basics of variational autoencoders in 2 minutes. So using this framework, how we can guarantee anatomical coherence. So that was the first work that did a PhD student that we co-supervised with Pierre-Marc. And I have to say that most of the ideas come from Pierre-Marc. So I deserve nothing on that. It was the start of our collaboration. So that's why I enter in the dance. So the first idea was to say, okay, based on tests so we use autoencoders to encode shapes. So it's no more numbers, but this is the mask, okay, that we want to retrieve at the end. We use variational autoencoders, and we realized that the two property, local continuity and global completeness, was needed to be reinforced, okay. So the idea was that we know, okay, when you have a segmentation of a full cardiac cycle, when you go from end diastole and end systole, you can imaging a time axis going from 0 to 1. So it provides you an information concerning the time in the cardiac cycle where you are. And it could provide a good information to the latent space to help to say, okay, the shape looks the same, but during the cardiac cycle, you are at that stage. So locally, it will reinforce the good properties, the continuity. So to do that, yeah, we just had a simple network here, okay, that force to have the good class corresponding to your image By class, I mean the time you are during the cardiac cycle. And by doing so, we have shown that it really helps to better control this latent space. And so we did the same experiments. So by the time that we created this latent space, then we just linearly take 2 points and apply linear tracks to go from one point to the first point to the last point. And this is the shape that we are reconstructed. So you see that locally you have something coherent, okay, and coherent also in terms of time propagation of the shape. Then the brilliant idea was to do that. So we work on the Camus dataset. So this is 500 patients, but for each patient we have 4 segmentations. So we have 2,000 images that we use to create our latent space. So it's not so much. And then the great idea was to use rejection sampling, which is a way to densify by estimating the PDF, the distribution that should fit the only 2,000 points in your latent space, okay? And thanks to this distribution, then we can sample as many points as we want. So we sample 5 million points, okay? So new points. And then from those new points, we reconstructed the corresponding shape. So this is this aspect. But we have no guarantee that the anatomical correctness will be guaranteed. So we needed to do a second step. We define 12 anatomical metrics. So nothing to deal with something that we have to differentiate to be integrated as a loss. Okay, it's only metrics. And very basic metrics that correspond to singularities that we can have sometimes. So for instance, that are represented here. So you don't want to have the structure. So here, for instance, the left atrium, which is inside the left ventricle. This is impossible. You can say there will no times there could be a hole inside the left ventricle. It's impossible. Or you can just have one myocardium in terms of region and not 2, so it avoids any hole and things like that. So we designed 12 anatomical metrics. And then in a fully automatic way, we just applied those metrics to the 5 million points. And we reject the one that do not follow this matrix. And by doing that, we keep 4 million points. So it shows that the rejection sampling did a good job, in fact. And so we have the guarantee that those points will reconstruct a correct shape. And then that's it. So you have a new image, you perform the segmentation, you check with the metric if something happens. If something happens, you just project in this latent space. You take the closest point, okay? Thanks to local continuity, it should ensure that the shape will be very close at the end to the one that you want to have. And then you just use the reconstructed shape as a correction. And this allows you to guarantee, well, by guarantee, it's based on the 12 metrics that we have designed, but we can imagine over metrics, that you will have something correct. So that was, I have 3 work to show you, and this is the first one. Not to go too much in details. Well, I don't want to expose the time. I used to speak too much, so I don't give you here the result in terms of number, but it was working quite nicely, and we published that. So you can go and see this paper if you want to see more details on the results. By doing so, this is great, but we haven't worked on the temporal consistency. So the second work is on the temporal consistency. To do that, we still use the versional autoencoders paradigm, but we use the one which is named RRVAE. So RR is for attribute regularization. It's something quite great that has been proposed, if I remember well, in 2021. And the idea is that on your image, so for instance, here with the numbers, you can define attributes that is meaningful. So for instance, the thickness of the number that has been drawn, okay? Or the slant of your number, okay? And by using this formulation, so by formulation, it's only you define a loss, okay, which is the attribute regularization loss that will guarantee that in your latent space, you will highly correlate some few dimensions to those attributes. And how to correlate that? You will guarantee the order that is measured in the image space that you will guarantee in your latent space. So for instance, if you have 2 9 values and you say this one, the thickness is bigger than image 2, it will be the case in this dimension. Okay, in this dimension, the value you will project, you will have a new value, but the ordering will be respected. Okay, by doing so, it's very interesting because then you can start to play with things that are very interesting. You have a number, so 9, you project, and then you just change the value in the dimension that encodes the thickness, and you can go from this to this, for instance. So you can have control on some attributes and play with that. So this is exactly what we did. So we start again with our mask. We define meaningful attributes in terms of anatomy. So for instance, for the left ventricle, the cavity of the left ventricle, we define the area, the length, the basal width, which is this, which is very important because this is where the blood flows. So the width is very important. The orientation for the myocardial, the area, and for the epicardial, which is this interface, the center, which allows to perform some kind of registration into the latent space, but I do not go into details. And so our latent space is composed of 16 dimensions, and half of them are linked to attributes. So we decided not to put only attributes to keep some flexibility in the kind of shape that you are able to reconstruct. And so then you can play with that. And so this is what I show you. So for people that do image analysis for a long time, it should remain you PCA. This is the same kind of things that we can do, but in a non-linear way, which is the big difference with PCA. And so you could expect to have more meaningful representation thanks to that, but you can still go back to this kind of PCA stuff that are very cool. So here, what we did is that starting from the same mask, then we just play by moving along one direction independently and see the effect of this ordering loss function. So for the LV cavity, I think it's quite clear. So you see it, so the left ventricle cavity is the red one. You see the influence, but also you see that it has a small but influence on the rest of the shape. So here on the myocardium. And this, we haven't coded anything on that. It's just something for free with this formalism. The same with the left cavity length, so the length of this contour. So you see how it influences. And what is interesting is that the shape that you retrieve is really something that you could have if you perform segmentation in echocardiography. Okay, so we have that. And now, what is the idea? The idea is to say, okay, I have my 2D NN unit, so I perform the segmentation independently frame by frame, okay? For each segmentation, I project into my latent space, okay? And then I will have a look at the evolution of the value along each attribute. And of course, if there is temporal inconsistency, we can clearly see it by analyzing simple 1D curve. And then, of course, do a post-processing on that, which is quite simple. It takes us some weeks to put it correctly. But then you just have to smooth curves and then reconstruct. And then you correct and you have your temporal consistency. So this is exactly what I just said. So for instance, here, okay, in blue, you can see the evolution of the left ventricle area over time. Again, we only apply 2D segmentation frame by frame independently, project into the latent space, compute those curves, and then perform smoothing, okay, and reconstruct the smooth version of the latent space and obtain the final results. And it works very well. So this is the kind of result that we have. So on the left, you have the segmentation of 2D NN units. And on the left, sorry, on the right, you have the output of our method. So you can see that we keep the shape accuracy, and we have now a temporal consistency. second piece of the puzzle. That's it. So now how to move on. So this is another example, but I will pass. So how to use that? So this is something that we have recently done. Now we want to go to the generalization aspect. So the idea is to say that it's very difficult to have manual annotation on the full cardiac cycle, but we can create gold standards. So for us, there is a difference between annotation and gold standards. Annotation means a human is performing manual annotation. Gold standard is a machine produce a result that is validated by an expert. Okay, so it's definitely, if you have a method that create very great segmentation and you just have to validate, of course, it allows to create gold standards on a large scale data set with less effort for a human. So this is something that is interesting. And so we really wanted to validate that in this study. Oops. So what we did is that, well, we build our puzzle. So we start with 2D NNUnet, learn from the Camus dataset where there has been manual annotation on 2 times in the cardiac cycle. We have shown that NNUnet perform a high accurate result on this dataset. Then we apply this result on a new dataset without, so the cardinal dataset, without any manual annotation. Okay, so we just apply our method. We correct it. Thanks to the method I just showed you that we name Castor. We get a gold standard, and from this gold standard, we learn 2 different methods to handle directly with the temporal consistency. So to give you the result directly without telling you all the different steps that we have done, we have shown that a simple 3D NNUnet learning from the volume, so the 2D plus T, so seen as a volume, perform very well, and this is what I will show you. Okay, the idea is that we have shown already that NNUnet is an architecture that is sufficient enough to perform nice segmentation in 2D. Of course, we wanted to try if it works also well, if you see the temporal axis as a new spatial axis and treat the full sequence as a volume. And it works very well, and I will show you the result. So the idea is that then we train 3D NNUnet on our gold standard and check what happens on a third data set. Okay. So this is the idea. So yeah, I don't know if I'm too long in terms of time, but I try to go fast.
No, it's okay. Yeah.
Okay, great. So every time we compare with the intra-observer variability, which give us the limits that we have to reach, and there's no meaning to go beyond that because expert cannot do more than that because of the property of the images. So this is what it is in red. So what we have shown is that if we use 90% of our gold standard, so CL means cardinal, so this is the data set where there were no annotation, we created gold standard, we learned from that with a 3D NNUnet, a 2D NNUnet, or a UNet LSTM. So we created another UNet with LSTM modules to take into account the temporal aspect. What we show is that we obtain very crazy results on this data set using a simple 3D NNUnet. So this is what I told you. Then what we do is that we learn from the complete gold standard obtained on the cardinal data set, and we go back on the Camus data set and we compare our results with the 2D NNUnet, which produce the best results, the current best results. That no, sorry, that's okay. I'm speaking here. Okay, okay, wait. No, okay. So again, so we compare, we learn on our gold standard from the cardinal dataset and test on the Camus dataset. So this is the results, and we compare with the 2D NNUnet here that has been learned on the Camus dataset and test on the Camus dataset. So we can expect that this is really the best score that will be difficult to beat, but you can see that we are very, very close, and almost also in the intra-observer variability. So this confirms us that this is the way to go, that thanks to our post-processing stuff, doing gold standard on large-scale data set and learn from that, allows to handle with different kind of distribution of data, depending on the vendors, depending on the whatever you want, and that we will be able to solve the problem of segmentation in echocardiography. Yeah, so this I will not give. So this is the kind of result that we obtain. So this is on the Camus dataset on the left, the Cardinal dataset on the right. Those two sequences has been acquired from a GE system. And here, this is the result that we obtain on another system, on the Philips system. Just for the story, what is great is that you can see that on the Philips system, when you extract the data, you also have everything that display on the screen, which is not the case with the GE system. But our method doesn't care about that. We can imagine that the distribution is not exactly the same because of that, but it can handle with it. And just one thing that we found very interesting is what does it mean when we say we are inside the intra-observer variability? For me, it means that you learn the hand of the expert, okay? And so we wanted to see if we were able to retrieve the scheme, the way that the specialist did the annotation, okay, on a different system. So here, this is the annotation. So the annotator, so this is not obtained by NNUNet, but this is the reference. The way that the annotator drew and performed the segmentation is not something that maybe other specialists can do a little bit differently, I would say, okay. Here, really, you can see during the contraction structures that appears that are difficult to see when the heart is relaxed. And the specialists made the decision to really follow those contours that appear end systole and extract them to say that the contour is there at end diastole. So you see, this is a particularity of this annotator. And this is exactly what happens here. So you see, we test on another system which has more contrast, for instance here, so where the structure, you can better see them. So we can expect that the distribution is not exactly the same, but even with another distribution, this particularity remains. So it's also a way for us to say that, yeah, effectively, we really learn the way, the hand of the expert, the way he drew the contours, and we reproduce this, whatever the equipment we use and the data that we are processing. Some few slides to finish about uncertainty. We also did with a PhD student that we co-supervised with Pierre-Marc some work on uncertainty. We used the CLIP framework as many people. And also, this is the idea of Pierre-Marc. So all the merit is there. I'm just the one who explains things, mostly. So the idea is that, okay, with CLIP, you merge image information with text. Here, the idea is to merge mask with the corresponding images. So we have image, we have the gold standard, so we have the corresponding segmentation. And the idea is to say, okay, first, from all the mask, I'm going to create variational autoencoders. So I will project into a latent space with, for instance, a dimensionality of M. For the corresponding image, we do the same. So we encode those images into a latent space, but with a different dimension, for instance, because it's harder to encode image than mask. And then there is a third transformation to project those points into a common latent space. And the idea is to say that, well, the mask that correspond to this image should be the same point in this latent space and far away from the other mask. Okay, so this is the idea of the cosine similarity here. So here in the diagonal here, this is the mask that correspond to the image and you want to maximize this value, so around 1. But the cosinus that you apply here, the dot product that you apply here, for the other mask, for these images, you want to be as close as to 0. And there is also a normalization step that is performed so that the norm of each vector is 1. So that means that the representation is on a sphere. Okay, so you are on a sphere. And one one image, the corresponding mask should be at the same location and very far away for the other mask. And this for all the possible combination. So this is the idea. And for uncertainty, what we did, inspired by the first work, and I have to say that it works pretty well. So we have a new image and you perform the segmentation of it. So the image is X star, your segmentation is U star here. Your image, you have the encoder so you can project and go on your co-latent space, okay? And then you can have a look locally, but locally on the sphere, and that was the key, one of the key of this method. Locally, you can have a look at the neighbors, okay? You will decode the neighbors that correspond to the mask, okay, that you have used to create your co-latent space. And then you will use those masks as the most probable shape that you should retrieve. And by a simple subtraction, you can measure the difference between your segmentation and the expected shape. And one key, as I say, is that here you see a weighted number, as this weighted number is computed to take into account the distance, but on a sphere. And you do the summation, and that gives you the uncertainty map. And just visually, it's very interesting. So we have tested it on different data sets, not only on cardiac data set. We perform the segmentation and we have the reference so we can compute the error mask, okay? And so what we expect is that if you are able to estimate also the uncertainty, that the uncertainty will look very close to the error map, okay? So visually, if your uncertainty map corresponds to the error mask or is very close, then you are happy. It's a simplistic way to see the problem. So here, this is with the name that you can see here, this is different method that has been applied that estimate uncertainty. And what we can see is that, and this is something that is known, the difficulty is that usually with neural network, your uncertainty is mostly like the contour of your segmentation with a few pixels, okay? So there's nothing to deal with the error that you obtain. For instance, here we can clearly see that the uncertainty map is only 1 pixel width. And he should have found more uncertainty here since there's a huge error there. This is the case for most of the uncertainty method that we have re-implemented or reused. And this is really what makes the difference with our method. So the name of the method is CRISP. And I don't know, here we can see that we have more uncertainty in that region, which correspond to the region where there's more error. You can see also this aspect there. And also in the segmentation of the lung here, you see that there's a strong error there and that effectively we have found here that the uncertainty is quite high also. For sure, if we want to improve those results, the big things to do and that we can do is to generate a co-latent space with more points. And those points, we can obtain them thanks to the gold standard way that we are able to do now. So this is things that we haven't investigated yet, but of course, it's very easy, and this is things that we want to do. Well, this is the result in terms of numbers, but whatever. And so, yeah, just to conclude, so we have used quite a lot the variational autoencoders framework to help us to design this puzzle, to guarantee anatomical coherence, guarantee temporal consistency, and to estimate uncertainty. For us, it's very clear that everything is there, and it's just now a matter to access and treat a large-scale data set, and this is what we are currently doing. We get access to 100,000 patients in terms of echocardiography, and we are currently applying this framework with more things like reinforcement learning with small human interaction, because of course you cannot check on all this huge data set if every segmentation that has been corrected are correct or not. So you have to make it automatic with as less as possible supervision of human. And this is things that our PhD students are working on. Thank you. Is there any questions?
Any questions? Jose?
Yeah.
Thanks, Olivier. I have many questions, but I won't take all the time. So for the work of uncertainty, we were talking this morning, we're working on this on many different similar things. Actually, it's interesting because Olivier and I were working with one student that we found exactly the same for the entropy, for example. When you have the uncertainty, it's actually, many papers are doing this Monte Carlo dropout, multiple inferences. And we found also that most of the time the uncertainty is coming in the boundaries, which is not the case.
Yeah.
Right? So I find it interesting that you also found that. So a question I have is that when you think about probabilistic unit, there's one word which I think is called stochastic segmentation by Ben Glocker.
Yeah.
They're also playing with these conditional VAs.
Yeah.
At some point from the latent space, you can generate multiple plausible potential segmentation, then compute the variance, compute that. Compared to these guys?
No, I used to say to Thierry that we have to compare with probabilistic unit, etc. We haven't done yet. One of the reasons is that
yes.
Yeah, well, but I think that we can also, the big question is that those formalisms, if I remember well, has been proposed to estimate the variability of annotation depending on the number of experts, but for the same image. So you have different shapes for the same image, and so you want to learn this variability in the formalism that has been proposed, and there are mostly no data sets that exists with several annotations for the same expert for each different image of your 2000 images. But I think that this formalism can be applied without all this annotation for one image. You can do that just with one annotation for one image. You apply this formalism, and then you sample many times. You have an image, you sample many times, you will have different results. You can also do that with diffusion model. That will, I saw recent paper doing that for estimate uncertainty. We haven't compared with that, definitely. So this is something to investigate, definitely.
Yeah, it's interesting. And another question I have for some mistakes. That when I think the first work is the work of Nathan, right?
And the second also.
The second also. One question I had at the point is that you have multiple metrics, for the post-processing, right? So you have latent space, at one point, you put it in the decoder and you get the segmentation, then you see if it's plausible or not, right?
Yeah.
So what about if you can use this information during training, like a loss? Because some of these metrics, they can be differentiable. For example, you think about the size or the soft size in this case, or you might have the length. What about if you can use it during training and you might avoid this post-processing instead because you are forcing the decoder or even the encoder to learn something?
Yeah.
At some point it's going to be plausible. And I think, if I'm not mistaken, I think Christian is something similar or doing something similar, like with some discrete losses.
Yeah, but we don't have any guarantee.
Yeah, I mean, that's what I was curious about.
We go on that way because we have the intuition that it will be easier to do like that because this is only post-processing.
Yeah.
And the post-processing will guarantee you somehow your result at the end. You don't have to think about derivative strategy to make it possible to package in a loss function, etc. So we can imagine trying to do that. It might be more difficult to apply it.
I think we can guarantee that in that case, because even if you force that, I think you will make some mistakes. I think it's purposely.
Could be. So there's more guarantee like that. And I think at the end, it's only post-processing, so it's quite fast. By the time that you have learned that, to apply it then in inference, it's not, the cost is not so much at the end. So, And in our case, the guarantee is very important because we want to use it then to create gold standards.
Yeah.
So in a fully automatic way. So this is something very important for us.
Okay. And just one very last question, very simple, I think. I was, when you're working on this high performing, values, you have a 90-something dies, like 94, 92, 95, which is the clinical value of this 1-2% difference. For example, if you have something, you say, okay, I have a method which is 93% dice.
Yeah.
Now I'm gonna spend 6 months in research to do something which is 90,
Yeah.
94, 95% dice.
Yeah.
We see a clinical gain of
Yeah.
these 2%.
Yeah, definitely. This is those value. The answer is really linked to the echocardiogram. The answer I'm going to give you is only true in echocardiography. In echocardiography, the first thing that we have done is computed the inter-observer variability, so between two experts. This is just a nightmare. Clearly, since the image quality is difficult, we realize that experts create their own experience over time, and they do not converge to the same results.
Yeah, but I would say it's high because 94%.
This is intra, not inter.
Okay.
So that's why to my student, I say, don't take into account inter-observer variability. There's no meanings. Sometimes, so you have two contours, the endo and epi, to create the myocardium. Sometimes when you compare the result between two experts, the endo corresponds to the epi.
Okay.
So it's crazy. So you don't have to take into account inter-expert. And it shows really, we discussed this morning, the importance to standardize that. So the guidance of the probe is something so important, and this is great that now things happens on that. So to make the acquisition and the measurement more robust, for sure. So this is why we wanted to, we went through intra-observer variability. So the level is very high when we did that, because we asked the same expert 2 months between 2 months to redo the manual annotation. And really here, what we wanted to capture is the level of accuracy you could expect based on the quality of the images. Okay, so the level is very high, clearly, I agree with you. But that was one of the success of this, because we put it the level very high, and we have shown that, I remember a lot of discussion I have with Pierre-Marc that told me, no, but don't try, it was an obsession for me to reach the intra-observer variability. Yeah, when we do research, sometimes we are upset, but yeah, for me, it was very an obsession, because the key message is very strong. It means you are able to reproduce the end of an expert. And we have shown it where we were the first. So the message is very strong. And that's why when then we go through 2D unit and then unit on the sequence, the result is almost done. It's almost there, because we managed to reach this level of accuracy. And so then the post-processing is even easier and stronger and robust, because the first step was very nice. So yeah, the level I think it's too high. If you say, okay, in clinic, what's the matter to reach that? But because I have in mind the rest of the pipeline.
Yeah.
But I agree with you.
Yeah.
And so the meaning is there. So you see here, this fluctuation, you are inside the intra-observer variability, because between two images, there looks almost the same, but you see a small fluctuation. So this is the meaning of the intra-observer variability. When you will compute, well, global value like ejection fraction or whatever, it will have no impact for sure.
Okay, thanks for that.
Yeah.
Any other questions?
Yes.
So, hey, how's it going? My name's Matthew Cave. I'm a professor at UCLA. I thought it was great. What? You got new hair, right?
We don't know him.
Yeah, but I work on ultrasound, real-time 3D ultrasound for cardiac, brain, abdominal, at the Harvard Medical School for several years. And so this is interesting. And I'm just wondering, like, are you going to be able to get better than intra observer?
Is there any meaning to be better than intra?
Because like humans are pretty bad, so you reproduce the human here. What will be required to actually improve upon that?
I really think that the problem here is not the human, is really the what you can see in the acquisition. As I don't remember.
So is there something that the human might not be able to see that the machine could see even better than the human?
I don't think so, to be honest, because okay, I have this one in mind. Even more in 2D. In 2D, of course, you have out of plane motion. Okay, the heart is doing exactly this motion. And so part of the structures disappears, appears, okay? You have a lot of artifact like shadow, hashing that happens that makes very difficult, and you have to guess where the shape is. And usually what did the expert is that they play the full movie. They see structures, as I said before, for instance, usually at end systole, since everything is contract, the information backscattered from the echo is more visible. And so you will better handle with the structures that you can see, and then you will track them and extrapolate the motion to say, okay, the curve is there. I don't see the information is not there, but thanks to the temporal consistency I learned in my head, I can say that the contour must be there, but the information is not there. It's not in the image. Yeah, there's a lot of study to try to improve the image quality. One of the key is the correction of aberration. This is something I really I believe in it, let's say, and the estimation also of the velocity of the sound velocity, because it's maybe a little bit technique, but for the reconstruction of the image, all the method make the assumption that the sound speed is the same, is homogeneous in all the image, which is not the case. That creates distortion, whatever artifact. And so there's a lot of works currently at 20 minutes from here at Palais des Congrès. I'm here for the conference on ultrasound images, and there's a lot of works on that.
What's the conference called?
IUS for imaging symposium.
Symposium?
Yeah.
Oh,
yeah. And so, yeah, the key might be here to have less artifact and better looking imaging. But yeah, no. So really, on what we did on Camus, I was the expert, okay, and then the cardiologist correct what I did, and I really spent a lot of time to be as accurate as possible. Not the time that cardiologists have during clinics; they have to move fast. So we thought that it would be better to have another protocol where we really take the time to take care of the structure, to do the best as we can, and I think we really reached the limit of the acquisition itself, and not the fact that we were bad drawers.
So the AI could probably not do better than a human on this data.
Yeah. But reproducibility is something very interesting, because two annotators will do definitely different
annotations. Yeah,
exactly.
Sure.
So here, okay, which annotator we have to trust? I have no idea.
Exactly.
This is not my question. Cardiologist has to put together and decide. But what we can claim is that at least if you design a very great data set and great 500 patients, it's not so much, and that you accept and you find a consensus on that, we can reproduce this in an ideal way.
So there's lots of cardiac conditions that occur in less than 1 in 500 patients too, you know, a lot of rare diseases and stuff. And
yeah.
Malformations of the heart.
Yeah.
Like this,
yeah.
Fascinating.
Thank you.
Maybe one more question? From a student?
They're all looking there. Okay.
So you select one person who's asking a question. That's what
It's okay, not big deal. It was clear. That means that the presentation was clear. So that's good.
Okay. Well, I have one question though. So when you were showing this post-processing technique of smoothing those measures, so was there one of these measures that was most important that smoothing was like? Have you did an ablation study where you would model them only one at a time and see?
Yeah. So what I can tell you, what was not expected for us, is that we get better results if we smooth. By the time that you detect that there were temporal inconsistency, so we design a method where you extract those curves and then you smooth them with the same method. Okay, so local smoothing. But then we apply this method to all in all the dimension, even the one that do not encode the attributes. And that produce better result than just focusing on the curve that you detected with temporal inconsistency. The kind of explanation is that what we have to deal with is that, okay, we have dimension that encode attributes, but it was very important also to remain dimension that encode anything. So for this flexibility I was speaking about, but those dimensions still encode information that is important, that we haven't tried to encode thanks to attributes, and that also need to be smooth over time to have better results. So this is this compromise between attribute information and flexibility. But at the end, yeah, the best result. So we did ablation study, but the best result was you have to smooth
everything,
all the dimensions.
Yeah, and how do you know if you're smoothing not enough or too much? Like
how to know? So we try to have a look at cases that do not happen so often, where there's a strong motion or things like that. And so we have shown that still it was working decently. Of course, we can lose a little bit, and this is one of the limitations. Since you smooth, of course, you can, you can smooth too much. So it's a kind of compromise, but yeah, in most of the cases, and when I say most, it's, I don't know, 90–95% of the time. Well, we haven't found things that were too smoothed by the method. So it might happen for sure, but this is not something common, I would say.
But could you sort of look at the like a histogram of gradients from a training set?
Of gradient of what? Sorry.
The variation of those signals, right?
Okay.
To make sure that those very sharp variations.
So we detect this peak. This is the way that we found if there are temporal mistakes or not. But those peaks, yeah, we have to find to fix at the end some limits to say, okay, this gradient is too high or not. And this has been done experimentally from the 500 patient where we have the annotation. So we learned the threshold. So this is of course this is a weakness. But yeah, you put the point where
well, maybe maybe in the Fourier space, I don't know. Like you could see whether some frequencies are just impossible to observe, and I don't know. Could be interesting.
But at the end, yeah, you will validate that in a statistical way.
Yes.
And so you will depend on the data set
Exactly.
on which you will perform that.
Yes. Okay. Well, let's thank Olivier one more time.
Thank you.